Harvard. And the wonderful aspect of the Black Hole Initiative that we have here is that it combines interest from different departments, different disciplines, physics, astronomy, mathematics, and philosophy. And if you feel that you are a little bit out of your comfort zone in the sense of not knowing some of the vocabulary, that's a good sign. It means that we are achieving what we aim at, which is to establish an interface between these different disciplines. And I very much look forward to hearing talks in mathematics and philosophy and enriching my vocabulary personally. Just a few words about the things that we have. So we are in the process of recruiting, hiring an administrator for the BHI. He or she, most likely he, would be, I cannot mention the name because it's not finalized yet, will be sitting at the end of this corridor to the left here, just to the left of the mural that Robert Dijkstra drew for us. And once the administrator is here, all questions about administration that have to do with visitors, that have to do with organization, securing this room, for example, for some events, should be addressed to that administrator. So that will make life much more comfortable for everyone. It just takes a few weeks to hire the person. We also have a very preliminary website that you can find by Googling the Black Hole Initiative. It's basically, right now, branches of the CFA website. And it just gives general information, but also we are recording all the talks using an iPhone. It turns out the quality is quite good. So these days, technology is really, it's quite amazing what such a small instrument can do. And that actually led to a project that is aimed at sending the guts of an iPhone to the nearest star. It's called Starship. Just because you can miniaturize all the electronics to such a, it was not used yet in spacecraft, but that's one of the features. What?
Is it something with a couple hundred?
No, not yet. None was launched. We are trying to launch. There are some issues to do with agreements between countries, but it's actually the way of the future, sending small probes rather than these big NASA missions. Anyway, so we are recording these talks, and we are posting on YouTube every BHI colloquium. Nina just informed me. Nina Zonneville is the lead administrator at the theoretical astrophysics division at the Center for Astrophysics. And she's currently helping us establish the BHI before we get the new administrator. And she just informed me that we now have a link on this website to all the videos. So if you miss one or you want to see it again because you work on something related, it's available on YouTube.
There are also links to the workshop that we had in April. We had a full day workshop and we videotaped all of that, and those are available.
So maybe if you scroll down.
Unfortunately, it's not letting me scroll.
Oh,
but
okay.
I promise you, if you go to that website, you'll be able to find it.
It's down there. There is a link where you can see the videos. A few other notes. On Thursday, we'll have a hackathon, it's called. Basically, a group of people will sit in this conference room and discuss ways of analyzing the data that will come from the Event Horizon Telescope. So the idea is, this is a project that is trying to get an image of the shadow of the black hole at the center of the Milky Way or other galaxies. And the data is getting in, and especially next year, thanks to the addition of another sub-millimeter telescope in ALMA, it will be quite exciting. There will be new data coming in, and the group is led by Shep Dolman is the director of the Event Horizon Telescope, but on Thursday, Michael Johnson will lead a group discussion here on how to use this data.
Yeah.
And everyone is welcome at 10:30, is it? Starting at 10:30 until?
Yeah, thereabouts.
About the entire day. Are you providing food? That's an important question.
Potentially.
We can accommodate that from the BHI.
Well, there's going to be a lot of food. Mostly, it's expensive.
Sorry.
Some people accommodate.
Yeah. Yes, and the other thing is we have a schedule for the colloquia, most of the colloquia throughout the semester, and there will be a link also on the website to that. Did I miss anything? I'm also in parallel working on speaking to wealthy individuals, trying to secure this initiative for many years to come. So if you're worried about these activities ending in 3 years, we're working on extending it far into the future. So it's great to have all of you here, and we'll start with the BHI Colloquium, and I would like to ask Ramesh to introduce the speaker.
Okay, so it's a pleasure to introduce our colloquium speaker, Pankaj Joshi, who is a senior professor at the Tata Institute of Fundamental Research, Mumbai, India, the premier research institute in India. So, Pankaj works in GR, space-time structure, notably singularities. I think of him as a mathematical physicist. He probably, I don't know. He'll tell us what he thinks, but I think of him as a mathematical physicist. He is quite well known for his work on singularities in particular. He's written monographs. There's a monograph, Cambridge University Press. There's another semi-popular book, Oxford University Press. He's got a Scientific American article. Lots of good stuff. Now, just to kind of, I think it'll come up in the talk. See, 40 years ago is when I first heard about black holes. And the things that I heard, which kind of stuck in my mind, are the no-hair theorem, simplicity of black holes, Penrose process, getting energy out of a spinning black hole, and the cosmic censorship hypothesis. And the guy who told me about cosmic censorship, he warned me, mathematicians haven't proved this. But mathematicians are very formal. They need everything to be proved. As a physicist to physicist, I can tell you, you can take this to the bank. It's up for Penrose, it has to be right. Penrose is cosmic censorship. That's 40 years ago. 20 years ago is when I first met Pankaj, and he convinced me in no time at all that the cosmic censorship conjecture is really dead, as originally said, because you can find clear counterexamples. He showed me many, and we have been looking at it over the years. So what's left is this cosmic censorship in its strong statement is dead, my opinion, but we can have a debate, and I hope there are people here who are interested who would like to talk with him. In my opinion, all that's left is to figure out how far should you weaken it before it becomes true. And I don't think we know the answer. Actually, I don't know the answer. Pankaj will be here this week and most of next week. So I hope we can have a conversation with him and have a discussion and try and figure out exactly what does cosmic censorship mean. Is it true at all? Good. Okay, Pankaj, tell us what it's all about.
Thank you. Thank you very much. I would like to warmly thank the Black Hole Initiative, the organizers, Professor Lloyd, and all of you for this wonderful opportunity to be with you and to talk about some of the work and research that we have been doing. Well, I talk of gravitational collapse, black holes, and singularities. Roughly the plan is a brief introduction, and then I would like to go to what are the recent developments on actual gravitational collapse studies, which is the process of a birth of a black hole, really. And then I will go to some other topics like observational distinctions on black holes and singularities, and it will finally try to relate this to black hole paradoxes, quantum gravity issues, stuff like that in a very brief manner. Okay, the key important issue in astrophysics, cosmology, and in fact in mathematical relativity or gravitation theory as a whole is what happens when a massive star, collapses at the end of the life cycle after running through its entire, nuclear fuel which was supporting, And the Chandrasekhar work actually began really, all of it, it would be actually quite relevant, to mention this remark made by Chandrasekhar way back in 1935, that the life cycle, life history of a star of small mass must be essentially different from the life history of a star of large mass. A star of large mass greater than this particular limit that we know now as Chandrasekhar limit for a long time cannot pass into the white dwarf stage, and one is left speculating on other possibilities. A very remarkable statement.
Why didn't he say speculating about black holes? Because,
It was not known
At that
What's
time,
the solution was now?
Oh, no, but Snyder and Oppenheimer were the first to argue that the collapse.
that's right.
Oppenheimer and Snyder.
I am going to come to that in a moment, but the real Oppenheimer Schneider paper black hole that really came in 1939. But that's why I showed the statement to you, a very sort of far-reaching statement that one is left speculating. Well, this is a statement. Let me just go on. Well, you are all aware. Ask me a question, or at the end, or I don't know what is the structure, but typically a star survives by burning its internal nuclear fuel, which is the supporting pressure, which resists the inner pull of the gravity. There is a balance, and then it's just like a balloon. If you release all the air from the balloon collapses because the internal pressure is gone. Similarly, once the internal fuel is exhausted, all the hydrogen to helium and so on, then finally the gravity takes over, shrinking the star. And then the key important point is, while the sun, star-like sun, they are living a much longer life, 5 billion, about 5 billion today and another 5 billion to go. The star of a large, 10 solar masses or so, it can't, endure more than a few millions of years. And therefore, what would be the final fate of such short-lived massive stars? This is kind of, a very important question and issue. And the important point is, as was just mentioned by Professor Lloyd, the key thing is to use the general theory of relativity, because when you are, collapsing a very massive star, then these are the strong gravity fields. You can't just get away by using the Newtonian gravity. You do that. That was done in 1939 by Oppenheimer and Schneider. However, their model was very idealized, interesting model. It assumed that, the density within the star was completely homogeneous. That is, from center all the way to outside is a constant density profile. Such a star is collapsing in time. And then, I better show a picture. Right away what happens is that at some stage the star is entering what is called the event horizon. Event horizon telescope was mentioned, and that is precisely the defining characteristic of a black hole. And then the star collapses, and finally it becomes completely dark, and the entire matter is collapsing at one single instant of time because it's homogeneous. So it collapses to a space-time singularity at given one moment of time. However, the important point is, as I will come in a moment, the event horizon has formed way earlier than the space-time singularity in this particular picture. So the singularity will be hidden within a black hole. All right, for 30 years, the subject was completely dormant. In fact, Einstein himself did not like, the Oppenheimer-Schneider idea. He wrote another paper saying that a star cannot collapse like this. There will be an equilibrium, and there will be a halt to the collapse and so on. However, it was later realized that actually the argument was not correct, and the collapse will take place and so on. However, the interest was dormant, and it was only in 60s with the discoveries, observational, of the active galactic nuclei, the quasars and so on. So much energy produced in that, how to explain that? And then, as was being mentioned, John Wheeler and others, gave the name black hole, and the Oppenheimer-Schneider paper was, well, I shouldn't say rediscovered, but a lot of interest grew. But physics and astrophysics of black holes, and then its classical and quantum aspects, interesting thermodynamics, many developments took place, as you are aware. I will just go on. So the key picture is there is a space-time singularity at the center. There is, the event horizon, and then many astrophysical applications were made. The jets and the accretion disks and so on and so forth. So black hole became the central engine of the astrophysics. To summarize this part, we have the paradigm that an average star will, this Chandrasekhar process via that will go to a white dwarf. However, for more massive star, you can have either a neutron star or a black hole. This was the kind of paradigm that was developed. Now I will just come to the recent developments on gravitational collapse. See, we made this scenario that any star collapsing will go to a black hole based on the Oppenheimer and Schneider calculation and the scenario. But the most important question in detail remained in the sense that suppose you have a star with a higher density at the center, which is typically the case. You see, actual gravitational collapse happens from inhomogeneous conditions, centrally peaked density, and then there is a collapse. So what happens? I mean, you have to work out the theory of that. Now, the key difficulty there was the complexity of the Einstein equations. There's a nonlinear second order PDEs, and how do you work out, the final fate of a collapse, unless you make so many specialized, assumptions, and that is what, led to, hypothesis, namely that any generic star will behave and act like the Oppenheimer-Schneider cloud only. That is, even if I collapsed an inhomogeneous star, even if I collapsed a rotating star, even if I collapsed a star with internal pressure, same outcome. That is the hypothesis, because in the Oppenheimer-Schneider case, even the pressure was taken to be vanishing. So many special assumptions. So any star collapse makes black hole only, hiding the singularity, the ultra-dense regions behind an event horizon of gravity. Now, let us just come to the gravitation theory, the Einstein theory. What we know, what we do not know. What we do know is that under reasonable physical conditions, certainly the collapsing star will terminate into a space-time singularity. So these are the well-known singularity theorems, and there are many related developments. A singularity will definitely develop. What we do not know is when, where, how the event horizons will develop, and when they will cover. For this we have concrete theorems. For this we thought that one fine morning, we will have a proof coming from Penrose, and then everything will be sorted out. But the general relativists, the gravitation theorists, were very well aware that this issue is live, even when all of the black hole physics was and is being was being developed.
A question. nowadays people can do numerical simulations of
Oh, yeah.
collapse.
Yes.
Do they see anything developing the way that spherical?
Yes, yes, yes. I'll come to that, but the key difficulty in the numerical simulations, this I have been trying to learn and discuss, is that when you go closer to the singularity, many of the codes really break down. So how to tackle?
But that's behind the horizon, so cosmic censorship doesn't mean that.
I'm sorry?
A proof of cosmic censorship doesn't need to know what happens in that region because it's behind the horizon.
Yeah.
If there is a horizon. The point is to test the
That is not an obstruction. Breakdown of numerical codes near the horizon is not an obstruction to numerical evidence for cosmic censorship.
Yeah.
Because you
Problem
can
is
stop your.
identifying the horizon, right?
Right.
Because you don't know, if you only run the code for a finite time, you don't know what it is.
Yeah.
Apparent horizon.
Yeah, the key
But
thing here.
apparent you can find locally.
Apparent
The key-
horizons don't mean anything, though, right? I mean,
If they exist, it means that they're inside a horizon.
yeah. Whether they exist or not is.
Let me just go on, I think, and then we can
No,
come
no,
back to
the
this
coordinate.
question.
No, you're right. That's actually.
Let me just go on, and we can come back to it, because this is a very important issue actually. I mean, I'll show you first the structure and so on, what all happens. When a singularity is visible and not covered within an horizon, you have to have a very specific criterion. And what happens typically is when you don't see an horizon but still go closer to a singularity, at some stage the codes break. But let me come back to it.
But wouldn't you say that the lack of any indication in any numerical simulation so far, together with 50 years of failures to find real counterexamples, I'm not talking about the Christodoulou thing, but real generic counterexamples, that should persuade that Yao should keep working, but that should be persuade physicists, astrophysicists, that cosmic censorship is a real thing.
Yeah, well, we have lots of collapse models actually worked out analytically, which actually show, either the formation or otherwise of the horizon. So we have very concrete, definitive
Isn't that what the
body.
Yeah, that's what we're
That's
talking
what
about.
the
But
topic is
I want to
about.
explain why this is such a critical issue
Yeah.
for Andy and others.
Yeah.
It's because if
Uh-huh.
there was a naked singularity, you could test observationally string theory.
Yes.
And,
quantum
and it's
gravity.
much better not to have a test, so that.
No, but
Andy, that was an insult.
no, but yeah.
Cheap shot, yeah.
And of course, we know that in the real quantum world that there are violations of cosmic censorship because of all that, right?
Yes.
So,
I think the time is up.
No, it's okay, it's okay. We can continue.
I'm supposed to warn him at 25 minutes.
all right, I'll shut
This
up.
is an important subject.
It is very important. That's why I said we
Thank
can have
you,
another
thank you,
discussion.
we can
A more
slide it.
detailed discussion later on.
It's okay.
Yeah.
Yeah, I'll be very happy. In fact, Michael, as for further details, I would be very happy to go into. Can I just for the moment, and then we can come. No, that's fine. These are very important issues. Oh, by all means. Yeah. So the key question remains. We do not have. Nobody sort of denies is that we do not have a proof as of today, of cosmic censorship. That I think almost everyone agrees, maybe. All right. So the important point that I wanted to make was the only way is back to basics. Just as Oppenheimer and Schneider did their calculation, similarly we have to work out more detailed, collapse models. And that only can solve. In fact, we ourselves wrote a paper, long ago, published in Annals of Physics, claiming a proof for cosmic censorship. But our assumptions were very artificial, actually. So we realized that this is not really, kind of a theorem, which will, pass as a proof for the cosmic censorship. So the idea is to examine very objectively the things. Actually, I do not like even the term this naked singularity. That also causes a lot of confusion and so on. But let me just go on. Lot of models have been worked out, analytic models actually, because there you have very clear and definite insight, and then the conclusion is that both the singularities which are covered either within the horizon or not, they both take place within purely the Einstein theory of gravity. Okay, right now I'm just constraining myself to that. To give you a very simple example, as compared to the Oppenheimer-Schneider scenario, which was purely homogeneous density, let me just introduce an centrally peaked density with ρ2 being negative. So the density is higher at the center, and then it slowly tapers off away from the center, and then you work out the details. The most important point that at the moment I want to point out is that you can work out fully the apparent horizon structure in that case. The apparent horizon structure immediately changes. I'll show you in a picture in a moment, but the point is that there is a term coming from the inhomogeneity, and what happens is that while in the Oppenheimer-Schneider case, the apparent horizon was decreasing away from the center. As soon as you have, for example, this ρ2 inhomogeneity, then there is an R square term which dominates, and that changes the structure of horizon, as I'll show you. This was the Oppenheimer-Schneider case. If you looked at the structure of trapped surfaces and the apparent horizon, then the apparent horizon was decreasing away from the center, as per the equation I just showed you. However, as soon as you allow for the density inhomogeneity, the simple one that I showed you, and this is the simplest generalization of Oppenheimer-Schneider model, then what happens is that apparent horizon becomes increasing. So earlier the trapped surfaces were forming way earlier to the singularity formation, and you can calculate all that. However, I have done nothing fancy, no ghost fields, no scalar fields, nothing. Okay, that is very important. I mean, otherwise you can blame it on that. However, as soon as I introduced the density inhomogeneity, then the apparent horizon becomes increasing. So the key point is the trapped surface formation is delayed. This is the Penrose, super-Penrose diagram. The singularity in the earlier case was, you forget this part, it was, you see, entirely space-like singularity. But now, with the introduction of the inhomogeneity, you have a null piece, a null singularity emerging. And what happens actually is that this is the typical coordinate picture. What happens is an entire family of future directed radial null geodesics emerge from the singularity. In the past, they terminate at the singularity, and in the future, they reach the faraway observer. And then many details have been worked out that I can go into later if there is interest. But the point is, you can work out the curvature growth, as you go closer to the singularity. How strong is the singularity? Is it fictitious? Is it removable? So on and so forth. Lots and lots of questions have been asked. I mean, the subject is full of, a lot of discussion and literature. However, the important point is that subsequently, many models have been worked out within, pure Einstein gravitation theory, collapse with different equations of state. The spherical collapse has been analyzed extensively from the perspective of black hole and naked singularity formation. Even few non-spherical models have been available. Self-similar and scalar field collapse have been worked out. Numerical models for star collapse, there was a reference to that, we can discuss that in a while. That has been done. Then there are related quantum gravity issues. Very important issues are related to genericity and stability. This is one of the most important feature in the entire game. I think I'm not sure I will have the time to go into the technical details. Gravitational waves from collapsing matter clouds. There are some connections, and then I would like to also mention some observational implications. But what I want to say is that if visible singularities do develop, if they are not always covered by the event horizons, then there are many important questions. They may be very exciting, or they may be, I don't know, on downside, whichever way you look at it. I mean, it depends on so the important point is you have to address so many issues, and the key sort of point that one is trying to make here is one is not invoking any special assumption. That is the most important point. Nothing brought from outside to create this. Otherwise, you can immediately blame it on that. The occurrence of the visible singularities, and that's the end of it. You work with pure Einstein theory. The thing is, you can now, in general, work out the structure of apparent horizons, what they are doing. Very briefly, I showed you, for the dust case. But even in general case, by general case, I mean the matter density, the pressures. So a cloud collapsing with an equation of state. We have been discussing P equal to K rho, in fact, and Ramesh and I. So you can write down the apparent horizon formation explicitly and in detail, and see that whether the singularity is fully covered or not. Typically, the scenario is something like this. You begin your star collapse from an initial surface at T equal to 0. You prescribe your densities and the pressures and so on. And then you evolve the collapse. The typical result is that subject to the energy conditions, subject to the regularity conditions, so on and so forth, there are evolutions of the Einstein equations which would take you either to a black hole or the other ones which would, where the singularity will not be covered by the event horizon. So this is the typical general feature. This figure corresponds to by the way spherical collapse, where we have done the work in full generality. But as I said, there are also non-spherical examples. Very briefly, the genericity and stability features. Well, the time is limited. We can discuss this only.
It's okay, it's an important subject.
All right. Thank you. Thank you. Thank you. So you see, what happens is, when a result is generic, suppose I have a naked singularity solution here. If I have a neighborhood, you see, in the space of solutions, which also have the similar property, then that is called, in some sense, a stable property. An open neighborhood should be there in a suitably defined, topology and so on. However, this is non-generic. All right. So in the dust case that we were talking, the black holes and naked singularities have this kind of features. We can discuss that more separately maybe. But the paradigm, you see, that you can ask is, neutron stars, white dwarfs, and this, whether you have black hole, fireball kind of situations. Little bit speculative picture. Well, very emotional subject, surely, just because maybe it is important. There have been, articles, there have been discussions. I ended up, writing an article. The contract I had signed had the title New Insights in Gravitational Collapse. New Insights in Cosmic Censorship. At the last moment, I was informed that the editors have chosen this particular title. I said, no, nothing doing. I'm not doing it. Then, but the, editors have felt, I said, no, nothing doing. Oh, it has gone to press. But you see, it puts me in trouble.
Don't worry about money.
No, what I am trying to say is, I don't see, just like black holes are black holes, singularities are singularities. I liked, this particular, this metal star galactica, some, serial is there. So the scientific editor just tells that it's just, naked singularity is nothing else, a black hole without horizon. That's good. Because you see, this is what the statement is. But the singularities are singularities. It is the event horizons, whether they are there or not, that is the question. All right. Let me just, the famous novel by some Chicago lawyer, which won many awards apparently. Well, very briefly, let me, respect the time, and the question is, there are two, camps, if I use this word, some people say that, all these models are nonsense, censorship should be prevailing in some sense. And then I say that let us use these models to, fine-tune the cosmic censorship. Because these models are concrete models. One is not arguing one way or the other. Let us use this model to fine-tune a better statement of the hypothesis. But then there are other people who just say that, why worry? They are there, let us explore the observational consequences. So, and then can we distinguish them? Look out there. Can you find these things there? That is the straight question that astronomers ask.
How is that different from the question of understanding the solutions? For example, if these are just coordinate singularities, then clearly they're not going to produce any interesting signatures, right? I don't see the distinction.
Well, if matter gets to infinite density, that's
I very briefly said that what you do is, you see, along
Try to
this,
understand the solutions.
Well, when you approach, this singularity along this family, it's a strong curvature singularity. It is not a coordinate singularity. By all means, that is a very big effort actually in the whole game. So it's a very genuine singularity, if that was your question. Okay, but let me just, say something just on this accretion disk properties. Other two, I think, topics I'll just skip. Suppose you have a black hole and a naked singularity configuration of the same mass, then the accretion disk properties were studied by several authors. And the very interesting feature that was noticed was that in the black hole case, there will be sharp cutoff, in the frequencies. When you, sort of consider the accretion disk, because there is this, ISCO, and there is a limit to the stable circular orbits. However, in the models which were naked singularity space-time, then the accretion disk extends way below the usually found ISCO, and then there would be, a very strong high frequency peak. All right, let me just not bother about these topics at all. There have been gravitational lensing studies, there have been particle collision studies, there are many details actually. Let me just not bother. I am coming to the end of my talk really. The key important point is, you see, we are now coming to, and that is my excitement too, of being here. This is wonderful, black hole initiative that you people have initiated. We are really, probing the very strong gravity regions now. What is the nature of this strong gravity regions? So that's your event horizon telescope, and well, this kind of phenomena can be explored in some detail actually. That is the hope, because the theory will go on as you say. However, the important point is, you see, what are the observational signatures which we are likely to get. All right, I don't have time to go into that, but recently I did this. Those who are interested can see some details of this. The main, I think the point is the following: even if the quantum gravity resolves the space-time singularity, the key difference in the two scenarios, if you accept they will occur or develop, then the black hole picture, it will be completely hidden within the horizon. However, in the other scenario, the ultra-strong gravity regions may be visible, for faraway observers to see. All right, I think we explored one, simple toy model of quantum gravity. We saw some, interesting behavior, a very rapid mass loss in the final state. To conclude, the theory looks like in reasonable shape. I think there have been very many papers. I think it is socially kind of supportive. If there are more papers and more people working, I don't know, it shouldn't be that way. But there have been a lot of studies on gravitational collapse in recent past several years. And I think people have studied modified theories of gravity and many other things. And then, okay, this seems to be on reasonable footing. Observationally, there are distinct signatures. This is just a very nascent subject developing, worth exploring. And then, if at all they are there, what will be the consequences and implications? Okay, so that's the, I think, end of my talk. Thank you very much.
Okay, very well.
Okay, I know you have to rush through the very end of the talk and observation signatures, but you can't leave us hanging. We are interested in the image, right? We want to look for the photon ring, and if there's an event horizon,
Yes.
the
Yes.
shadow.
Right.
How does that get modified?
In fact, in some of the naked singularity models also there are photon spheres.
Okay, that's what I thought, but can you tell us what determines it, and when there is a shadow, when there isn't, when there is a photon?
We are just beginning, so far
We
we were.
want the answer.
I think we need to, why don't you join?
I'm happy to join, but what I mean is when you say it's observational
Yes.
distinguishable, is there any
Yeah.
example you can give us?
I gave one accretion disk, I gave
That was
that
the-
example,
yeah.
then you see other two topics I just skipped, gravitational lensing.
Uh-huh.
So, the trajectories around the black hole and the naked singular are very different configuration. So we worked out in, a couple of papers, 2-3 papers. I can give you the references if you are, I'm here, so,
yeah.
I mean,
Okay.
anytime, and, if there is interest, I can, we can, I'll be very happy to give more details, and it will be wonderful, lot of education for me, frankly. I am just, a little bit of analytic things I have done, computers and numerical, all these things I wish to learn, observational things. Yeah, but I think it's a
Basically,
very...
he's saying you do it. He's got the solution. You calculate the photon orbits.
No, yeah, also I will, talk and learn. Yeah, that would be the kind of, yeah.
So, Pankaj, I want to make one comment,
Please.
and I'm sure there'll be a lot of disagreement here. To me, it seems there are two issues. One is, what does the real universe do? Do we actually form naked singularities or not? And I think there the answer may well depend on actual properties of matter, the equation of state, what happens at nuclear densities, how does P go versus rho, all of these questions may come in. But then there's the other side, which says, look, here's a beautiful theory called general relativity. It's mathematically well defined. Does this theory actually permit naked singularities to form or not? That's the answer that I think a mathematical approach can answer. And to my mind, at least you have found a number of special solutions. They are also generic in the sense they have some range of parameters. How general, we don't know, but I think that's really the result. Even though Pankaj would like it to be and Feryal would like it to be related to real objects, that may or may not exist. We don't know.
But remember, there seems to be a mismatch between what the perception is in the community that Andy expressed, and I also am familiar with that. There are no viable solutions for making it.
I found out 20 years ago that there are.
Okay, so Andy.
Any number.
May I?
Yeah.
Is that a viable physical solution?
I'm sure y'all do it always.
Penrose made it, there was some precise mathematical form of the cosmic censorship conjecture, which was counterexamples were found, and then there were more refined version of it. You know, you have a problem like you just have a dust crossing singularity, right? You have
That's
a
not a
perfect-
real singularity.
Yeah.
So you first of all, you have to, when you make your conjecture, you know, you have to rule out that kind of thing.
What is
And so
that?
it's a-
What is that?
Well, you just have a.
That shell crosses.
You have a,
yeah.
you can arrange some initial data with some collapsing dust, where it will reach infinite density.
But-
It's like
and
a
finite
shooting charge
time.
in
So
electronics.
Exactly,
it's highly non-trivial to make a conjecture that doesn't,
But what about
that doesn't have
physics?
immediate
Yeah.
counterexamples.
In fact,
Okay,
this.
So the actual conjectures are extremely, I don't even understand any of them, they're extremely hard to even state.
Absolutely.
And
There is no state.
and the early ones that were made were wrong, and then they had more refined versions.
Exactly.
Lulu found some counterexamples. However,
You have said it.
despite all this, in 50 years of discussion of this, the lack of any sort of really good generic counterexample that didn't involve fine-tuned initial data, or and maybe the best counterexamples were Christodoulou's naked singularities with the lights out. The lack of
Similarities are
any
what
real,
Pankaj has found.
the lack of any generic counterexamples together with any appearance of it in numerical
May
think makes it
May I make-
implausible.
May I make a?
But we should try to prove it as a
But-
mathematical
I
fact.
mean,
We should
but,
probably state and prove it.
But foaming
If I
density
may-
profile, centrally peak density profile is a pretty generic.
Well, but I think the disagreement is Andy does not recognize this as a proof yet. Or, I mean, is this a well-known
I
demonstration?
think a centrally peaked dust cloud
Yes.
will make a naked singularity, okay, if it's spherically symmetric.
Yeah.
This is, I think, beyond doubt, because it can be proved analytically, so that is.
And that's a physical
Yeah.
singularity.
Yeah. It
Absolutely,
is a
it's a
physical,
strong
absolutely
correlation.
physical singularity.
That's not true finally.
No, it is. I mean,
But it
generic-
does.
We see
no,
that.
generic means an open set.
Yeah,
in the
yeah.
space of all solutions, and that is not.
No, that it is.
No, it's not. It's spherically symmetric.
That's the thing.
Okay, yeah, well, see, this is,
What's the problem with spherically?
yeah, good. I am happy. I am very happy with this
a
comment.
repeat. It's a repeat. The original objection to Oppenheimer-Snyder was precisely that it was not generic,
Yeah.
right? They could only solve it with spherical symmetry.
And what's the problem with spherically?
No, but that's a tiny, you're going to a
People
very high
thought that
dimension
it was
space.
argued by people like Einstein, I don't know who was arguing.
Michael,
that if you.
Why don't you plan another?
This is before any of us were alive.
And
That
why
if you
not
put
all the,
terminal level,
why not we have the
it
opportunity
no
to,
longer,
right now I
this is
don't
what
have.
Penrose and Hawking and others proved is
Good
not the
point.
case, that it's,
You have
that
generated-
an open subset of initial data, that you get a black hole. And I don't know the precise way that cosmic censorship should be formed, but
And these solutions, if you perturb them, the spherical solutions are not giving you a singularity if you perturb them. They are unstable.
There are some non-spherical solutions too,
Okay.
which do produce.
So I think it's worth continuing this discussion.
Yeah, so
Yeah.
let me just say, this is perfect. That's why this initiative was started. Pankaj is here both this week and next week, and what we're hoping is to have a second seminar that's more technical, where we can hash out these issues more. So please.
Let's not make it a seminar.
Or
Blackboard
discussion.
discussion. Whiteboard discussion.
Yeah, well, there's one.
I'll be more than happy, in fact.
Yeah. So if you're interested in coming to that, please write, and we'll try to schedule something that works for everyone. So let's thank Pankaj.
Thank you very much.
So our next speaker is Alex Lupsasca, who is a graduate student in the Harvard Physics Department, working primarily with Andy. And today, Alex is going to tell us some recent work he's doing studying the appearance of hotspots orbiting near an external black hole.
Thank you for letting me speak here. I'll give a brief talk with no equations, only pictures, and hopefully less controversy. So the topic of my work,
Or just try.
I'll just try. I'll try to have pictures for you. So this is ongoing work with Sam Gralla, who was recently a postdoc here and is now faculty at U of Arizona, and Andy Strominger. I'm going to describe the first part of ongoing work, which will also, I think, result to another paper with another grad student, Lily, whose office is right here. She knows about all this, and hopefully, eventually, we'll collaborate with Michael to produce a template for the EHD. So, what is this calculation that I want to tell you about? Well, we've been studying black holes theoretically for a very long time, and now we finally have the prospect with the EHD of really seeing what they look like. And it turns out that answering this question, okay, I take my camera and I snap a picture, I point my telescope to a black hole and I take a picture, what do I see? It's actually vexingly difficult to answer, as most people in the audience already know. It's not a straightforward application of the curve metric or the tools that we usually employ in our theoretical studies. But I want to tell you about this calculation, which in fact we can do analytically, as opposed to most of the work that has been numeric. But we have to do the analytic work, we have to go to a particular regime. So there's a few words that I highlighted on this slide, and I'm going to explain exactly what they mean and how they're relevant to our problem. So the first thing is that we're going to try to compute the optical appearance of a hotspot. So a hotspot is like the Green's functions version of the problem. It's just light up one point near the black hole and say what image you get from this one point. The interesting thing is that, of course, if you have a more complicated source, you can just reproduce it by having multiple hotspots. So this is what I mean by when I say this is the Green's function version of the problem. So we're going to describe the optical appearance of light emitted from near the black hole, but in order to be able to do the calculation analytically, there's two ingredients that I'm going to need. I'm going to need to be near extremality. So that means that the black hole has to spin very, very fast, and I'm going to come back to this. And the other thing is that the emission has to come from near the ISCO. This is an acronym, which means innermost stable circular orbit. It turns out that if you consider particles orbiting in the equatorial plane of a rotating black hole, there's a final radius at which particles can orbit circularly and stably, and beyond this orbit, they just fall into the horizon. So for instance, if you have an accretion disk of matter swirling around the black hole, the accretion disk would really terminate at the ISCO, and beyond that, the matter would just fall in very quickly into the black hole. Okay, so these are the ingredients I'm going to need. So to make the setup a little clearer, this is really a very naive cartoon of what you would naively expect to happen if you didn't know about gravity and bending of light. So what we're imagining here is that we have a black hole, which does have an event horizon. I'm going to assume there's an event horizon. I painted it in black. And I'm going to consider a hotspot that's orbiting very near the event horizon of the black hole, because in the setup that I'm studying, that actually ends up being where the ISCO is. So I'm going to have a hotspot very close to the black hole in the equatorial plane going around. And I'm going to look at this situation edge on, which means I'm also in the equatorial plane, staring straight at it.
By the way, you are making another assumption, which is the pressure forces are negligible, which for fluids they are not necessarily. So you're assuming that this one.
I'm assuming the technical assumption is that the particle is going on a geodesic.
Right.
It solves the geodesic
It's
equation.
true perhaps for a very thin accretion disk, but the minute you make an accretion disk thick, there are pressure forces that affect the orbit.
Okay, that's
Just to keep in mind.
for further work. We can go beyond that. So if there were no gravity and we just ray traced in flat space, light comes at you directly, what you would naively expect to see is this. So this is the percentage of the period that you're in. So for half of the period, the star or point source or hotspot is coming in front of the black hole, and you see a dot moving from left to right. And the other half of the period, it's behind the black hole, and you don't see anything. Okay, this is obviously not actually what you see because we've totally neglected gravity. So once you take into account the effects of the geometry, you see a completely different picture, which is actually literally orthogonal. So what you see instead is this. And when I say that you're orthogonal, I mean that the apparent image of the star is really going, it's moving vertically, not horizontally. So I want to emphasize this is actually exactly what you would see. This is an analytic computation whose result is a movie of really what you would see in the optical regime if you were to look at the black hole with the hotspot orbiting near the ISCO in the extremal case. So there's a few features in this picture that I'd like to explain very briefly because perhaps I imagine not everyone is familiar with this. So the first thing is I've added this red curve on this picture. This is the black hole shadow, which some of you know about. I guess everyone has heard about it, but may not know exactly what it means. So let me first briefly tell you exactly what this is. Let's assume, schematically, we're looking at the black hole from above. So it's now spinning around this axis. And we shoot light from various angles with different impact parameters. If the light ray is far away, it just gets deflected. If the light ray comes very close to the black hole, it falls in. But there's a boundary case where if you tune the impact parameter just right, the light ray will sort of graze the black hole and circle around this line forever. So this is what this trajectory is almost doing. So there's a surface which is called the photon sphere, and Pankaj was talking about it, which is the boundary between the region in which light rays can approach the black hole and escape again, so they get deflected, and the region in which this can no longer happen. So if you have a black hole and there's a source of light that illuminates it, shines light on it that gets deflected to the HT, you're only going to get light rays of this type, because if light rays go within this sphere, they're going to have to fall into the black hole so there can be no deflection and you don't see anything. So this is to say that on this picture, all the light that comes from sources far away from the black hole will appear outside this red curve, which is therefore the shadow. This argument does not apply to emission that comes from very near the event horizon. So as we're going to see, if you have a hotspot near the event horizon, the light that it shines out can come out directly at you, and so it evades this argument, and it can appear within the shadow, as we'll see in a second. So that's one aspect of this picture. And it's important to emphasize that if you have a slowly rotating black hole, the shadow is basically a circle. But when the black hole spins up and approaches the maximal allowed spin, you have this line that develops on the end. And in this picture, the black hole is spinning this way. So what happens is that the space-time is being dragged around by the black hole, and so the light gets beamed at you here, and you get this interesting geometrical feature. So this was known to Bardeen in the 70s, who plotted this picture, and also had an argument that showed that if you're emitting in this near-extremal regime light from near the event horizon, it can only come out within a very small region near this line. And the closer the source is to the event horizon, the more constrained the image is within this range. So that's the basic feature. Now, why are we string theorists or people in the high energy theory department working on this? Well, I wanted to show you on this plot certain trends. So what you see here, on the x-axis, you have the spin of the black hole, how fast it's spinning. So at a equals 0, you have a Schwarzschild non-rotating black hole. And when a is equal to 1 or 100%, you've maximally spun up the black hole. And this line is the radius of the photon sphere. So this region beyond which no light can bounce back at you. And then the other radius that's interesting is for a particle that's co-rotating with the black hole, there's this ISCO radius beyond which the circular orbits no longer exist. And that's on this picture RMS. So that's the last radius at which you can have a particle that orbits stably. And so what happens is that as you near extremality, all these curves appear to coincide, which means that all these radii appear to be superimposed. So how can that be? Well, the schematic picture due to Bardeen that we should keep in mind is one that looks like this. So we have an asymptotically flat region, which is far away. And as we approach the singularity, as we get closer to the event horizon, which is R plus in these pictures, well, the space-time gets curved, and we get a throat of the black hole. But in the limit where the black hole spins infinitely fast, this throat gets deeper and deeper and deeper and deeper and deeper. So you have a region of space-time that emerges, which is an infinitely deep throat. And in fact, even though these spatial radii appear to be the same coordinate radius, that r equals n in this case, there's actually an infinite proper distance between them. So if you're trying to simulate the situation numerically, you're in a little bit of trouble, because to be able to resolve the difference between these radii, you need a grid on your computer that gets increasingly fine, but in the end you always get killed anyway. So it seems a little bit difficult. Of course, in principle it could be done, but I think Hotaka, who's a postdoc here, and I were trying to match our calculations, and it turns out that this particular regime I'm about to show you, it's not quite reachable through pure simulations. But what's nice is that precisely in this regime, where we have an infinite throat that develops, we can use a special symmetry that emerges. It's called conformal symmetry, that allows us to compute many things analytically. And this tool has been used to constrain the force-free magnetospheres of black holes, to compute gravitational wave emissions, even from stars plunging. But in this particular project, obviously I'm talking about the image. So what is this conformal symmetry? Well, in a nutshell, we know that under black hole thermodynamics, black holes have a temperature. And really, if you dial this knob, the spin, if you vary the angular momentum of the black hole, under the analogy with black hole thermodynamics, it's like turning up the temperature. It's adjusting the knob of temperature. And when you spin up the black hole all the way to extremality, it's under this precise correspondence, it's like dialing the temperature to 0. And so in condensed matter physics, this is well known. There are these critical temperatures at which conformal symmetry arises. And in fact, this is exactly the same story. You dial in to extremality, it's like going to 0 temperature, you have an emergent conformal symmetry. And we can apply the same kind of reasoning to solve various problems. If the mass goes to infinity,
the temperature also goes to infinity.
Okay, I haven't thought about infinite mass black holes. But just to give you a very quick picture of what's happening, you see this throat gets infinitely deep. And so what happens is you can just cut off this part of the picture, okay? And now you have an infinitely long cylinder. And the cylinder has a new symmetry, which is just going up and down the cylinder. Now going up and down the cylinder means going to larger or smaller radii. So this translation symmetry of the cylinder is actually a dilation symmetry. So in this spacetime, you have a new symmetry which has emerged, which is a dilation symmetry. And moreover, if you imagine an infinitely long cylinder, which is striated by these lines, you can move each of these lines independently in an angle-dependent way as you go around the throat, and the cylinder still looks the same. So that's a local scale invariance, which is exactly what conformal symmetry is in pictures. And so what we've done is use the fact that the space-time geometry is very simple in this region to solve the geodesic equations analytically. And then again, when you're far away from the mouth of the hole, you're basically in flat space. So again, the geodesic equation simplifies and you can solve it analytically. And then this was actually first done by Andy and Achilles Porphyriadis, who's now with Santa Barbara, and Lily. And what they understood is that there's a method to connect the geodesic that you solve for here, the geodesic that you solve for here, to basically be able to do the ray tracing, to solve the null geodesic equation everywhere. So this is what we've done in this project, and now I can show you finally the features of this image. To better understand what's going on, I'm going to zoom in on this part of the picture, and here's what it looks like in detail. So again, this is the percentage of the period that you're in. This faint line is the edge of the shadow. Now, on the other side of the shadow, there's lots of light that comes from various sources away from the black hole. But there's direct emission, which comes within the shadow. That's that corresponds to light rays that never had a radial turning point. They just came out straight at you. And so what you see is that, again, the star is moving on a periodic orbit, but you actually see its image. First, there are multiple images, and you see them for more than half of the period. This is a little bizarre. And this is a regime in which, here I'm working with a star that's still far enough away that numerical simulations can match this kind of behavior. So this is the end of numerical simulations, as people can do them nowadays. And then last step, I'm going to show you what happens when you push the star even deeper into the throat. So what's going to happen is that you're going to get this kind of crazy image. Now, each of these dots is an image of the star, but the light was emitted at different times in its history. And so you have multiple images of the star that appear simultaneously. And there's lots of very interesting features that appear. So let's zoom in. This is my last slide. I'm just going to zoom into the top here.
This is falling into the black hole?
This is just a hotspot on a circular orbit near the ISCO of the near-extremal black hole.
Is it just extraordinarily redshifted?
Yeah. What are the intensities of the different points?
So we can also compute the intensities analytically. It's kind of, you know, I didn't show the equations because they're incredibly messy, but we have formulas for them. Now, if you tune into extremality, the intensity goes to 0, but if you're slightly away from extremality, it's not 0. There's a fall off. We know the rate of the fall off, and we can give the intensities of these dots. Actually, the intensity appears to be peaked near these edges. So the last thing I want to do is just show you some of the.
And this includes some overall multiple orbits.
Yeah, yeah. So here I've let the star spin for a very long time. In the beginning, it takes a very long time.
Photons multiple orbits.
That too. Yeah.
Isn't there a possibility for infinite number of select images?
Yeah. So the dots here are colored by the number of times that the photon has gone around the axis of symmetry before it reaches
can go infinite number.
And the limit, as you push the star deeper into the black hole, it takes a longer and longer time for the light to come out, and it spins an increasingly number of times. Yeah, there's divergence.
So
Alex, have nothing to do with any of the characteristics.
No, the colors correspond to how many times the light went around the axis of symmetry.
Wait, so Alex, what are the dimensions there? I mean, how far across?
Good. So in this picture, what I'm doing is that I'm zooming in on this corner of the image. So the height is always fixed. It's always this height. It's
it's like 1/4
of the
of
mass of the radius of the black hole.
Mhm.
But the width decreases. So it's roughly, this comes from the fact that emission that comes out of the throat is constrained to be near the superradiant bound of the black hole, and so that means it has to come out. The deeper the star is in the black hole, in the throat, sorry, the deeper that you put the star in the black hole, the narrower this window gets. And so
most of the stuff is going to be at the top and the bottom, is that right? It sort of looks like a parabolic.
Yeah, it's going to look like some kind of eyes. Yeah, and so to show you the last picture, I want to zoom in on this top corner. There's a lot of interesting features. So this is the top corner of the previous image. Again, this is the percentage of the fraction of the period that you're in. And what's interesting is that the whole system is periodic. So the images have to behave periodically. But what happens is, even though the collection of images is periodic, if you track this blue dot, at the end of a period, it becomes the yellow dot. And then at the end of this next period, it's taking a little bit of time, it's going to become the green dot. So the images collectively are periodic, but there are signals. There's a time variability in this signal, which is actually not said by the mass scale of the black hole. It's much longer, it's redshift. Okay, so I've run out of time. There's a lot of interesting features here.
So as it goes around more times before that we get something that's more redshifted in the light that we see.
Well, there's two different ways to understand your question. One is, if I push the star deeper and deeper into the black hole,
Yes.
yeah, the redshift changes. It never goes to 0. There's always an observable, that we have to talk about exactly what can be seen. But there's always light that comes out. The redshift does change. And what also changes is the redshift is not the same up and down this curve. It also depends on how high the curve is.
questions afterwards?
Afterwards. Well, maybe one more question, Bob. Yes, Bob.
Yeah.
Well, no.
Well, okay. Perhaps just one quick question for Alex before we transition.
But this just seems very interesting, because I think we maybe talked about this before, but you could have a situation where different parts of the image correlate with other parts of the image on timescales of the orbit, right? So you can get photons coming to you from the black hole that correlate on timescales of half an hour for a Sagittarius A star or something like that.
Yeah,
It's
so,
like a storage ring of photons in the sky.
so I was always in the equatorial plane, but we can do these calculations at any angle. The image is always reflection symmetric around the apparent equatorial plane. And so there are always multiple images of the star, which appear at different places in your sky, but which actually were emitted, correspond to light emitted from the star simultaneously. So you could look at different places in the sky and see light that was emitted by the star.
They correlate.
They're correlated, exactly. Yeah.
Okay, let's think Alex.
Thank you.
And apologies that we are running a little behind. Fox saying that. Well, anyway, do I understand correctly? You want to use the whiteboard for the talk?
Yeah, so I thought we'd be downstairs, so I made the mistake of preparing a chalkboard talk. So if like these three people, if these three people could just move, I think everyone else is fine.
I think we can also maybe we can move people out, yeah, and this line. Okay, so you are the first whiteboard talk at the
We have a black one. That's a white.
Yeah.
Which one did you put?
I think this is simpler.
Oh, you can choose the one.
I think for simplicity. I just think it's simpler.
Well, this is as used to astrophysicists, the black hole.
I know.
You have to understand the culture.
Okay, so
We don't
Bob
want to get too
Penna.
cozy.
Okay, so Bob Penna was a graduate student at the CFA working on simulations of accretion disks with Ramesh and others, and then a Kaplan fellow in MIT, and now I think you're at Columbia. Okay, so take it away.
Thanks. Okay. So this talk is called Spinning Black Holes in Hyperbolic Space. So black holes in hyperbolic space. Okay, this is joint work with Scott Hughes, who's at MIT, and Stephen O'Sullivan. And the motivation is, again, came from astrophysics. The astrophysics problem was thinking about binary black holes and tidal interactions. So specifically, we have a small body going around a black hole. It'll deform the event horizon. It'll create these tidal bulges like ocean tides. And depending on whether those bulges lag or lead the orbiting body, you can get torques just like the Earth-Moon system. And so you can have energy extraction from the black hole or energy going into the black hole, depending on. And there's a good theory of this at low black hole spins, but at high black hole spins, it's still being worked out. One conceptual problem at high black hole spins is it turns out if the black hole is spinning very rapidly, the event horizon has no isometric embedding in Euclidean space, so you can't visualize it, and you can't visualize these tidal bulges. So to get physical intuition and to be able to visualize these processes, we've, it turns out you can embed the rapidly rotating black holes in hyperbolic space, 3 space. So that's what I'm going to describe. So recall that the Kerr metric has an event horizon at the radius of the event horizon, and the usual Boyer-Lindquist coordinates is this guy. And this can create the misleading impression that the black hole is just always a round sphere because it's at some constant radius. But of course, this is just some coordinate. Let me introduce this dimensionless spin parameter, A over m. So this is that thing that goes between 0 to 1, depending on how fast you're spinning. And what you should really do to think about what a black hole looks like is you should take the Kerr metric and you should project it onto the event horizon. And so then the event horizon is this 2-dimensional sphere. You get some 2-dimensional metric on that sphere. And so looking at that metric, you can compute its Gaussian curvature. And so if you just have a non-rotating black hole, so A star is 0, then the Gaussian curvature of the horizon is just a constant equal to 1 over the radius of the event horizon squared. So indeed, a non-rotating black hole really does just look like a round sphere. However, if the black hole is spinning, then the Gaussian curvature of the horizon is no longer a constant. So if I define this coordinate u to be cosine theta, so that it's -1 at the south pole and +1 at the north pole, then the Gaussian curvature of the horizon is a function of u. If the black hole is not spinning, it's indeed just constant. But now if I let the black hole spin, the Gaussian curvature of the event horizon varies with u. And it varies such that, for example, if I have a black hole with spin parameter 0.7, it's more curved near the equator, so it's larger, and it's become less curved or flatter near the poles. So that spinning black holes, the rotation causes them to look flattened out. So this is what you should picture when you picture the event horizon of a spinning black hole.
Bob, when you say curvature,
Yeah.
this is just looking at spatial components. Is that right? What kind of curvature
Yeah,
is
so if you take the curve metric and project it on the horizon and maybe take a constant time slice, so you just have just the theta phi part of the curve metric is left.
part of the curve?
Yeah, so if you take your curve metric and just plug in r equals r plus, so all you have left is the theta phi part. Yeah, and that theta phi part won't be the usual round metric and theta phi coordinates, it'll be some messier thing. And this is what it looks like. If you make the black hole spin really quickly, then this Gaussian curvature actually becomes negative near the poles. And really quickly in this case means that you make A star greater than √3/2, which is about, what is it about? 0.866. And so there's definitely black holes in nature in this regime. But it turns out in this regime there's no embedding of the surface in Euclidean 3 space, so you can't visualize it in your head in the usual way. Let me briefly try to explain why that is. So why can't you embed this in Euclidean ordinary flat 3 space? The way we usually visualize surfaces is sitting inside a flat space. Okay, so let me remind you what Gaussian curvature is. So if you just have a curve, then you define the curvature at a point by finding the best fit circle at that point, looking at the radius of that circle, and then the curvature of your curve at this point is 1 over that radius. So the way the Gaussian curvature is defined for a surface, if you have something like this, you want to know the Gaussian curvature at a point, you look at normal sections, which are curves sitting in your surface. You find the ones that extremize their curvature as curves. You compute those, curvature as curves of these two things. And then the Gaussian curvature is what you get by multiplying those together. So for a sphere, if you want to know the curvature of a sphere, the Gaussian curvature is 1 over r squared, because the principal curvature along this guy is 1 over r, and the principal curvature along this direction is 1 over r, and you multiply those together. So that's just the non-spinning black hole. If you have a cylinder, then one of the principal curvatures is 0, the other one is 1 over r, and so the Gaussian curvature of a cylinder is 0. A saddle has these principal curvatures are bending in the opposite sense, so that's why saddles are negatively curved. And so what's going wrong here at very high spins is that sitting in the Euclidean space, the poles want to be saddle-shaped locally. But you know that a black hole event horizon is a surface of revolution. And so it should also have this axisymmetry. But sitting in Euclidean space, you can convince yourself that you can't make a saddle also axisymmetric. And so you just can't put it in Euclidean 3 space. But it turns out you can put it in hyperbolic 3 space. So let me explain that. Okay, so so you can't put it in Euclidean 3 space, which is just flat 3-dimensional space. But remember, you also have hyperbolic 3 space, which is the thing that has constant negative curvature everywhere. And then to complete the family, there's this spherical 3 space with constant positive curvature everywhere. And there's actually a family of these parameterized by a length scale L telling you how negatively curved they are, this constant negative curvature. And it turns out where here, the Gaussian curvature is kappa 1, kappa 2. Here, the intrinsic curvature of a surface becomes kappa 1, kappa 2 minus 1 over L squared. So you can put things in here where their principal curvatures are bending the same way, and yet the point is, and it's and yet it still has negative curvature because of this factor. And so this is why we can put our rapidly spinning black holes as surfaces in here, and we can visualize them. Let me explain that in a few more words.
Do those ISCOs, whatever they are, the minimal orbits,
Yeah.
exist for these very fast spinning
Oh,
black
for
holes?
sure. Yeah, they have ISCOs too.
So you would still see something that was.
Yeah, so what you see on the sky with the Event Horizon Telescope is this photon orbit, with things related to the ISCO. And there, yes, it all spins. You get a black hole shadow, which you can see with the Event Horizon Telescope. The difference between what I'm talking about here and the Event Horizon Telescope is there, the image, these light rays have propagated through the whole space-time on their way towards you, and so the image has become deformed by the intervening space. My pictures that I'm drawing in this talk are more intrinsic pictures of the horizon, just as an abstract surface. In some sense, more intrinsic to the horizon because they're not muddied up by the intervening space. Yep.
Yeah, so I also wanted to make that distinction when you actually do solve the geodesic equations around even like whatever
Yeah.
the horizon looks like, it actually looks the same. But that
Yeah.
has been done. I'm
Well,
not
different
talking about
spins.
Alex's maximal.
Yeah, I mean, at different spins, the shadow
You can go to
changes.
0.99.
Yeah, for sure. I
and
agree.
still, your
Yeah.
shadow is pretty circular.
Yeah,
Your
pretty.
shadow and your.
Yeah.
I mean,
Yeah.
you really start.
I
Like
agree.
you have to start adding quadrupole moments to get it to do anything other than being a circle.
Yeah, I agree. Yeah. Okay. All right. So let me talk about this a little bit. So H3. Okay. So mathematicians have given us lots of nice models for getting intuition and learning how to think in hyperbolic 3 space. So the metric of hyperbolic 3 space looks like this: 4L squared, that curvature length, over 1 minus R squared, and then here you should just put flat space. Just remember what the flat space metric looks like in spherical coordinates. Here, this R coordinate runs from 0 to 1. So you can draw a picture of H3 as just a ball, or if I ignore one of the dimensions, just a disk. And so this boundary of the disk is R equals 1. This is called the Poincare disk, or the Poincare ball. Geodesics in here just look like circles which begin and end on the boundary and are orthogonal to the boundary. And so this is this way of visualizing this constant negative curvature space. And once we get intuition for how that works, we can draw pictures of our rapidly rotating black hole event horizons inside there. So another important category of shapes
Bob,
in here. Yes?
This is an auxiliary space. It's like
That's right. Yeah.
But there is a flat space can be written in hyperbolic coordinates, right? It's like the Milne universe, right? You can foliate flat space-time with hyperbolic.
Yeah.
With
Sure.
hyperbolic slices.
Yeah.
And so, might there be some? Might there be some representation of Kerr in hyperbolic coordinates in which this hyperbolic space is actually the real space rather than just the
for sure.
auxiliary embedding space?
So one question I got when I was just talking to someone about this informally was, what do you mean, just a way of rephrasing Andy's question, what do you mean, this surface doesn't fit in Euclidean 3 space, like there's lots of spinning black holes out there. The ambient space near the horizon is not Euclidean 3 space, which is why the surface can live there. And like you're saying, it's more like something hyperbolic, and maybe there's a way of foliating it so it looks like this. Does that mean that's kind of what you're saying?
Well, I think it would be a mathematically very natural thing to do to write. Minkowski space can be written.
Yeah.
That's what Milne did, right?
Yeah, sure.
The Milne universe is a quadrant of flat Minkowski space written in hyperbolic coordinates.
Yeah.
So if you took the Milne coordinates, asymptotically Milne coordinates instead of asymptotically Minkowski coordinates, maybe this
would
extra
emerge more
auxiliary
naturally.
coordinate could just be the radial coordinate.
Yeah, good comment. Okay, one other natural thing in hyperbolic 3 space are things called horospheres. So a horosphere is a sphere with one point touching the boundary. And the reason they're important to know about is that they have 0 Gaussian curvature. So once I have intuition for H3, I can start embedding my black holes in there. It turns out you can embed any surface in H3 if you make the hyperbolic length scale small enough. So by sticking to Euclidean space, you're somehow limiting yourself and only seeing a small number of the surfaces that exist. If you put a Schwarzschild black hole in here, it just looks like a round sphere like it does in Euclidean space. Fun fact, if you put a unit mass Schwarzschild black hole in a unit L equals 1 hyperbolic space, the Poincare radius is the golden ratio, just for fun. So you can tell it's a beautiful subject. But I don't really have a good explanation why. Yeah, the Greeks knew that. Now we can draw extremal black holes though. So if you increase the spin of this black hole, it just becomes flatter and flatter. If you make it extremal, so A star equals 1, it looks like this. Now if this was an egg sitting in Euclidean space, you'd say that's positively curved there. But you can convince yourself it's not by drawing a horosphere. So a horosphere, look, is this sphere touching the boundary. It has 0 Gaussian curvature. And so since this is less curved than the horosphere, it's negatively curved. Whereas this guy is more curved than the horosphere, so it's positive. So if you play around with these pictures, you can actually start to get intuition for how things work in hyperbolic space. And you can visualize your tidally deformed black holes there. And so I don't have time to go through our whole thing of going from black hole perturbation theory with a tidally deformed black hole to the movies. I'll try to show you a movie. But let me just finally mention one interesting step, because it's just mathematically interesting. So the black hole perturbation theory calculation gives you the Gaussian curvature of the perturbed event horizon. And one of the steps we need to do is we need to reconstruct the metric. So that's just an interesting math problem. So black hole perturbation theory gives you some Gaussian curvature, the Gaussian curvature of the perturbed horizon. And one of the steps in our process is we need to reconstruct the metric on the perturbed horizon. So we need to go to the metric. And this turns out to be kind of interesting. So you can always write the metric on the two-sphere as like this. I guess I don't need that. E to the 2u g bar. So there's this thing, the uniformization theorem, that says you can always write your perturbed metric in terms of your unperturbed metric. It'll always be related by a conformal factor and some diffeomorphism. And so the problem, and we know the unperturbed metric, and we know its unperturbed Gaussian curvature. So to find g given kappa, it turns out you can, when you phrase the problem as find this phi and find this u, you get a nice differential equation, which you have to solve this differential equation, minus 2u delta u, this is with respect to g bar, minus kappa bar equals kappa of phi. So we need to look, so we know the unperturbed Gaussian curvature, we know the perturbed Gaussian curvature, we got that from black hole perturbation theory. We need to reconstruct the metric, so we need to find this u. And there's also a phi sitting around here, which creates trouble. But the surprising thing that I don't fully understand is we're always able to find solutions where phi is just the identity. And it's not obvious that that should work. But let me give you an example of what happens. Just consider A star equals 0. Look for solutions with phi is just the identity. And can take the perturbed curvature, which we know, expand it in spherical harmonics, say CLM, YLM. We're looking for this function u to reconstruct the metric of the perturbed horizon, expand that in spherical harmonics. It turns out, when you solve that differential equation after linearizing it, you find this very nice simple formula that ALM is CLM over L plus 1 minus 1. And so you can always find your ALLMs given the perturbation and reconstruct your U using this simple formula in this simple non-spinning case, provided you don't have any L equals 1 modes. And it turns out, because of the spin-2 nature of the gravitational field, your black hole perturbation theory can always be set up to not return L equals 1 modes. And so for black holes, the perturbed metric will always be in the same conformal class in some sense as the unperturbed metric. And it's not just some general thing for, it's not true for all surfaces. For all surfaces, it's not true. But it's true for black holes that if you just perturb them weakly, the perturb metric, you can find a perturb metric in the same. So it's just kind of this funny thing. And it wouldn't work in higher dimensions because you wouldn't have this uniformization theorem thing. So that's something maybe that, like, for mathematically minded people, I think is kind of interesting. And then the last thing is I'll just show you a result. So here's a result. Here's my perturbed black hole. Here's the Poincare ball. There's r equals 1. This thing has a star equals 9999. And this is perihelion. When the perturbing body is at its closest approach, if I can get rid of this. So the black hole is maximally deformed. It's Gaussian curvature on the surface. It's yellow at the poles because it's negatively curved here. And you can just make movies as the thing goes around on this elliptical orbit. You can just watch how the tidal bulges evolve as it goes back to an unperturbed black hole. Because now the thing's out at aphelion, the perturbation.
This is the perturbation.
So this black hole has a little body going around it, and that little body's raising these tidal bulges. Yeah.
And bulges reflect something similar to a fluid, or things like that?
Yeah, so it's behaving just like a fluid.
What kind of equation of state is a fluid? Equal rho?
No, kind of weird one. There's actually no rho. Yeah, it's kind of weird.
Is the volume conserved?
Yeah, so there's, you can read about all this. You can do all this in membrane language, yeah.
Is the volume conserved in the surface?
Is the area of the surface conserved?
Yeah, during the perturbations.
I mean, in general, no, because you'll have gravitational waves going in and the thing is getting bigger. In this calculation, I don't remember.
Okay.
Couldn't you arrange for this to have no quadrupole?
Couldn't you arrange for this to have no quadrupole? I don't see why.
There is always a cigar shape, right?
Yeah, I don't think so. I mean, this is not no hair theorem stuff because this is not a Kerr metric. It's black hole perturbation theory. It's a deformed black hole. It's genuinely deformed.
Okay, let's think
Yes.
about. So are you around this afternoon if people have more questions?
Yeah, for a little while. Yeah.
Everyone is welcome to hang